Alright guys, this is section 3.2. In this section, our goal here is to be able to solve linear systems algebraically. One of two ways we can solve linear systems algebraically is using the substitution method. The step one for this kind of method is to be able to solve one of the equations for one of the variables, either x or y, whichever is easier. The next step is to be able to substitute the expression from that first step into another equation and solve for the other variable. And then finally substitute the value from the second step into the revised equation for step one and solve. So let's look at how we can use the substitution method in order to solve a linear system. So with this example, I have 2x plus 5y equals negative 5 and x plus 3y equals 3. I see that I have x all by itself. Okay, since it's all by itself, it's easiest to use the substitution method and solve for that x. So what I want to do is move that 3y to the other side and solve for x. So when I move that 3y to the other side, I get negative 3y plus 3. Okay, now that I have that x, what I could do is take that and substitute it back in to the other equation for x. Okay, so I got 2 times x, but now we know that x is negative 3y plus 3. And then the rest of that linear equation was plus 5y equals negative 5. From here, what I want to do is distribute. So I'm going to distribute that 2 to the negative 3 and to the positive 3. So 2 times negative 3y is negative 6y, and 2 times 3 is 6. Then I'm writing or bringing everything else down. I have like terms here, so negative 6 plus 5 is negative y, plus 6 equals negative 5. And then I need to move that 6 to the other side, so I got negative y equals negative 11. But I want positive y. Right now there's a negative 1 right in front of that y, so I want to divide that out of there. So now we got positive 11 for y. Okay. Since I know what y is now, what I could do is substitute that y back in to either the y in the first or the second original equation. It doesn't matter which one. I'll just pick out that second one because it was a little bit easier. Okay, so if I do that, x plus 3y, but y is now 11. That's what we figured it out to be, equals 3. Well, 3 times 11 is 33, still equaling 3. And if we move that 33 over, 3 minus 33 is negative 30. Okay, so here's my x, and we have the y. So in the end, our solution here is negative 30, 11. What that means is if I plug negative 30 and 11 for an x and a y back into my linear system, then it will satisfy both of those equations in that system. But there's another method too that I could use to solve a linear system of equations algebraically. The first step with the elimination method is by multiplying one or both. Okay, one or both are very, very key words here. I can multiply one or both of the equations by a constant to obtain coefficients that differ only in a sign for one of the variables. Okay. In step 2, we're going to add the revised equations from step 1 and then combine like terms by eliminating one of those variables. So our goal here is to eliminate one of the variables, either x or y. And then we're going to solve for the remaining variable that's left. Then step 3 says, okay, substitute the value obtained from step 2 into either of the original equations and solve for the other variable. So let's look at one of those. So we're going to use the elimination method to solve this linear system. Okay, so looking at my x column here, or my x's, I see that I have 3 and 6. Okay, 6 is positive right now. 6 is a multiple of 3, so what I can do here for this whole system is multiply this whole thing by -2. Okay, by -2 because I want the -6 to appear so it can cancel out when added to that positive 6 that's in my second equation in my system. So if I go ahead and multiply that top linear equation by -2, I get -6x and then 14y because two negatives make a positive, and then after the equal sign, -20. Make sure to multiply on both sides of the equal sign by the whole thing. Now I'm just going to rewrite my second linear equation underneath, and I'm going to add them together. -6 plus 6, that's 0. That's what we wanted. We eliminated one of the variables. In this case, that was x. 14 plus -8 is -6y, or positive 6, excuse me. Positive 6. And -20 plus 8 more is -12. And to get y by itself, well, I just need to get rid of that 6 by dividing, and -12 divided by 6 is -2. Okay, so now I could take that -2 and plug it in to either of the y's in my original linear equations. It doesn't matter which one you choose. I'll just go ahead and plug it into the bottom one. So if I do that, 6x minus 8 times y, but y is now -2, equals 8. So I got 6x, and then -8 times -2 is 16, equals 8. I'm going to move that 16 to the other side. So I got 6x equals -8, and I need to divide by 6. So x is equal to -8/6, since that fraction has two even numbers in it. They both can be divided by 2. That's the same thing as 4/3, and it was negative. So my solution here, the x value was -4/3, and the y value was -2. So again, all that means is that I can plug -4/3 in and -2 back into both of my linear system, or both of my equations in my linear system, and it would satisfy both of those to make true statements there. So we've been having pretty normal numbers equal out in the end, but what happens if we get to a situation where we have something that looks like 5 equals 12? Okay, well, when solving the systems of equations, it's possible not to get even answers at all. Okay, so if we get something like 5 or 15 equals 12, or even 4 equals, say, -6, or anything along those lines where both sides of the equal sign really don't equal each other in the end, that's just no solution. You could also write this as a big 0 with a line through it. That also means no solution. And even if your equation gets down to something like 15 equals 15, or -7 equals -7, then their answer is just all real numbers. Okay? Not no solution, all real numbers. In our last example here, we're going to be solving this system again using elimination. Okay, and just looking at my x's first. Well, let's see an x and 3. Okay, if I want to use elimination, I can make that 1x look like 3 by multiplying it by 3, and if I want to eliminate the x terms, I can use it with a negative. Okay, so -3 times stuff. So if we do that, -3 times 1x is -3x. And Negative 3 times negative 2y is positive 6y. And negative 3 times 4 is negative 12. Okay, then I'm going to put down my other linear equation that I didn't do anything to. Negative 3x plus 3x is 0. 6 plus negative 6y, or 6y plus negative 6y is 0. So they're both 0 on the left-hand side. And negative 12 plus 8 is negative 4. Since this statement is not true, or basically it is false, this is a no solution. Because 0 does not equal negative 4. So if you get to this point where they don't equal out in the end, that can be a no solution. But if they do equal out in the end, then it can be a situation where the answer is all real numbers can satisfy that linear system.